I'm going to be talking about the volume electron microscopy community, but with a focus on data. So in case you don't know what volume electron microscopy is, it really comes from the 1980s with this study, which was the mapping of the mind of the worm with Sidney Brenner's team, who had the problem that they needed to follow neurons over long distances, but they needed the resolution to see individual synaptic vesicles and synapses. And so they needed electron microscopy, but most of EM is done on very thin 2D sections. So what they did was to take multiple sections, about 10,000 through the worm, pick them up onto EM grids, and put them into a transmission electron microscope and image them one by one. And in the 1980s, that took them 10 years. So things have changed a lot. Yesterday, I was very honored to visit an EM facility 7 minutes walk away, where Dr. Gabuto has one of the automated versions of this called grid tape TEM. And they're doing amazing imaging over thousands of sections automatically fed through the TEM and spitting out petabytes of data. And there are different ways that you can do volume electron microscopy. So it's kind of a catch-all term for a group of techniques where we can grow cells on cover slips, or we can take pieces of tissue, we embed them in resin, and then we start taking sections. So where we take sections and put them down onto a substrate, we use the term array tomography. And then we can use either a TEM or a scanning EM here to image every single section in order. And then we take those images and we build them up into an image stack. There's a second group of techniques, which we call block face techniques. So we can start in the same way with cells or tissues, embed them in resin. But this time we take the block and we put it inside a scanning electron microscope, which has a very large chamber. And so we can use different methods to start imaging and then cutting inside the chamber. Here with a diamond knife in serial block face scanning electron microscopy, or using a gallium ion beam or a plasma ion beam, which can then cut much thinner sections. But again, we're generating these stacks of images, which we then put together. And if you'd like to use these videos in your talks, then they're made by Kedar Narayan at NIH, and they're all available to use freely on the Volume EM website. So the output of our work is these stacks of images which we can scroll through. And for Volume EM, the community at the moment has defined VEM as continuous volumes greater than 1 micron, which differentiates us a little bit from the thin sections and the cryo-electron tomography field, but we hope to connect up across scales to work with them. So if the 1980s was the mind of the worm, we're now in the era of the mind of the fly. And this study just came out. And Bill told you a little bit about this kind of imaging earlier in the week. And the developments that have taken us from the mind of the worm to the mind of the fly have rolled out across all other areas of the life sciences. So you now find volume EM in neuroscience, other neuroscience questions in cell function, plants and marine life, in studies of infection, and also on imaging human tissue. So the community that have come together, this really started, the current community in 2019. It started over dinner at EMBL EBI in Cambridge with Ardan and Gerard and I, and Luigi Martino from the Wellcome Trust, discussing that we really needed to come together and discuss the issues that were facing the field, particularly with big data. And Kedar Narayan, who brought together 50 experts in the US at NIH at around the same time to discuss challenges. And the community is extremely friendly, extremely active. And here you see everybody getting together at our town hall during the pandemic on Zoom. And you can see we have a beautiful logo designed by Jemima Burden at UCL. The community have put out a lot of different resources. We have the Volume EM website, just search Volume EM and you'll get to it. And that brings together a lot of those resources. We had our first Gordon Research Conference last year in Ventura in California. I think some of you were there, which was amazing. And we've renamed it Ventura. And we also have a number of publications. So if you're new to the field, you could look up this primer on volume electron microscopy, which explains all of the fundamentals. And we have a number of training videos online to help you with the tips and tricks which you really need to get up and running. There are a lot of resources, and I can't talk about them all today, but in terms of data, I wanted to give a shout out to, oh no, I've lost a name. Okay, sort that out. Matthew. To the team who've put together a sample preparation widget, which is on the Bioimage archive, and it helps us to input our very complex sample preparation metadata into the archive so that it can be related to the image data that's deposited. We have 6 volume EM working groups. We have volunteer co-chairs for each, and everybody who's co-chairing in the groups are volunteers, so they're doing this in their extra time. And we're very grateful to the Chan Zuckerberg Initiative, who have funded us as a community, led by Kirk Zimick and the co-PIs here, who have really taken the efforts to the next level. And one of the things, so this really started with a big push in the UK. So one of our aims was really to make this much more international. And you can see that over the past few years, we've had a big push to connect with a lot of volume EM facilities across the world, which have a number of different technologies. And you can see that we're really bringing in collaborators from all over the world now. And last week in the UK, in Harwell, we had our first volume electron microscopy technology forum, which was bringing people together to talk very detailed hands-on about the techniques and what needs to be done. And I would just like to call out to anybody who's local, because version 2 will be coming in 2026. It's going to be held in Asia Pacific, and the organizers are Alice Liang at New York University and Kun Song at Peking University. So if you're interested in being involved, then please either speak to me or drop Alice an email. So the thing with volume EM is, even though it's 3D, we're still imaging very tiny fields of view. And so we need to use other imaging modalities to help us target. And what you're seeing here at the top right is so this is one of our own projects, is a human kidney biopsy from a transplant rejection patient. And the biopsy is 1 millimeter in diameter and 8 millimeters long. And if we tried to image it just with volume EM, it would take us 50 years. So we have this project to try and reduce the time to 5 days. And we do that using X-ray microscopy to image the entire biopsy, so we can target regions of interest like glomeruli and single immune cells involved in rejection. And then we image with electron microscopy. And what I'd like to highlight here is the software that we're using to navigate this really complicated multimodal data. So this is something called MOBI, developed at EMBL Heidelberg by Christian Tischer and his team. And so what you're looking at here is scrolling through the X-ray data, which was collected at the synchrotron in Hamburg. So we can image both hydrated biopsies and resin-embedded biopsies extremely quickly in 2.5 minutes, including the data reconstruction. The biopsies come back to us and we immunolabel them. The red here is the immune cells. And then we take those slices and we send them over to Yannick Schwab's lab at EMBL Heidelberg, who's in charge of speeding up our volume EM. And what you're seeing here in the Zoom, which I didn't feel brave enough to do live, but we can use MOBI to access the data remotely through a web server, is individual immune cells, which we can now say the red ones are CD16 positive immune cells, and the ones without red are immune cells that are not CD16 positive. So our correlative is allowing us to target, but it's also giving us cellular identity. And just to give the team who worked on this a heads up. So I had a chat with Asta and asked what was the most useful thing, considering we're talking about data today. And she said, well, use it as an opportunity to call out for what we need in volume EM. And there's a slight caveat here that this is from the viewpoint of me. So this is a biologist microscopist who needs help with most things data-wise. So very quickly, we need sustainable support for big data handling software, and we are absolute supporters of the next gen file format. So we're using OMESR in MOBI. We need support for our community to more broadly deposit their data in the public image archives. So we put our data in, but we would like to see everybody depositing their data so that it can be reused and obviously properly labeled with metadata. We've been generating benchmark data sets. So here we've got a correlative light in EM benchmark, which we use to develop some automated software to register light in the EM. And that's gone up to Empire. And I think that kind of data is extremely useful for AI development. And we can generate that at the microscopy end, but it comes with a cost, so we need support for that. We need full integration of the LM, EM, X-ray, and ion imaging communities. So a little experiment, if you can give me a couple of minutes. I promise I won't go over. So hands up anyone who uses a microscope. Great. Please keep your hands up anyone who uses an electron microscope. Great. And then please keep your hand up if you would describe yourself primarily as an electron microscopist. Whoa. Okay, good. Kildare, it's just you and me. So I'm not sure the rest of this is going to work, but Kildare, do you use light microscopes as well? So what we tend to find is electron microscopists use light microscopes as well, and sometimes X-ray microscopes, because of this need to target. But I think it's not necessarily true the other way around. If you're a light microscopist, you don't necessarily use an electron microscope or an X-ray microscope. So maybe have a think about why. And we shouldn't forget X-rays and ions, because it's much more unusual to hear about those imaging modalities at conferences. And I think it's really important that we all become multimodal imaging scientists. But then I have to test my assumptions. So as a question to you, do you think that we should all become multimodal imaging scientists? And just to mention some funding we have from CZI, which is trying to address that. So the idea is to build a correlative light and electron microscopy pipeline, which is easy enough that it can be used in a light microscopy facility without the need for an expert electron microscopist. So this would put correlative into the hands of light microscopists, and also by removing a lot of the complex equipment and workflows and toxic chemicals and reducing the cost, then we can put this into lower resource settings. And this is a huge piece of work. So just to show you the teams involved, so this is work with Paul French and Ricardo Enriquez and Amy Strange, our software engineering and AI, and Ben Luz, who has our first VP Clem kit and will be helping us to test it remotely. We also need community consensus on standards for correlative and multimodal imaging. So I haven't even finished this network of what imaging modalities can be connected to which ones, because it took so long, I kind of got bored and I started doing other things. I will do that because it's insane. And actually, there's not really agreement on what correlative or multimodal means, and we need that soon. And we need user-friendly tools that have support for deployment at the NTWE level. Can anybody guess what that means? So that's not terminal window enabled, which is me, so I can't even type into a terminal window. So don't overestimate how few skills in your complex data areas some of your end users have. So I think we're all guilty on software and hardware development of spending a long time on the development and thinking that the deployment is going to be easy. And when we're talking about deployment, we really need to get things into one button push and drag and drop, which the Crick is being done by Amy's team with something called AI on demand, which has Nextflow behind it, and which allows us to just pick models like MitoNet, drag and drop our data in, and this is some focused ion beam data collected with Ben's team and Nicola. So this is correlative, with all the mitochondria segmented out. But even now, I can see that some of these mitochondria need joining together and some of them aren't correct. And so my homework for this trip is to correct it all. And I'm going to do that in Empeñada, which is also a tool from KDAR. But I also had to have Martin spend 3 hours with me to get me up and running. So we need to reduce that down. So finally, from the mind of the fly, we're now in the era of the mind of the mouse. And the scale is insane. If you're interested in the challenge, we wrote a report with Greg Jeffress at the LMB, and that tells you what we think needs to be done at every level. But the thing you'll be most interested in is that by far the biggest cost is likely to be proofreading, with current technology estimated to be $7 to $21 billion. And I think that's why last year Volume EM was named one of the technologies to watch in 2023, alongside things like the James Webb Telescope, which we're still dining off as a community. So please do have a look at all of the resources, and if you can, join us for next year's edition of the Volume EM GRC in Barcelona. Thank you very much.